Continuing investigation of basic data structures, um, this time I'm going to start talking about the second basic data structure that is interesting in itself and also is used as the underlying data structure for more complex data structures that we will see later. The data structure is called linked list. Now, in this video, I'm going to only talk about concepts. I'm not going to uh, go into the details about the implementation, but in the next video, I will implement this in C++. Now, the prerequisites that you need to have to be able to follow this video uh, is, first of all, knowledge of C++ pointers, because uh, that's one of the um, fundamental aspects of implementing linked lists, and also C++ classes and objects. So I'm not going to explain those, but other than that, um, I will explain every detail conceptually in this video, and then the implementation in the next video. So here we go. The idea of a linked list is that you have these entities. So first of all, the kind of linked list that I'm talking about in this video is called singly linked list, for a reason that becomes clear in a few minutes. But the idea here is that you have these entities called nodes, and each node consists of two member variables. So node can be implemented as a C++ class, and it has two member variables. The first member variable, sometimes called data, sometimes key, is what you're storing in that node. So for simplicity, for now, let's assume that those are integers. So I'm going to store, say, 10 this node. And then also each node has a pointer. And this pointer contains the address of the next node. In other words, it points to the next node. Again, the next node, similar story. It has some integers in it, 7, for example, and the pointer that points to the next node. So that's why it's called linked list. And it's called singly linked because each node is only connected to the next node. Now, later on, we will talk about doubly linked lists, where each node has a pointer that points to the next and a pointer that points to the previous node. But that's for later. Okay, so let's say here 8, and then this pointer points to the next node, and pointer, and let's say 15. Okay, so this is a linked list with 4 nodes, and the data or the key in the nodes are 10, 7, 8, and 15, and each node has a pointer. So if the type or the name of the class is node, this will be a node star variable, and it contains the address of the next node. Now, the idea is that if you can find the first node, then from the first node, you look at this pointer that is stored in this object, and with that address, you can find out where in the memory the next node is stored, and then from there you can find out where the next next node is stored in memory, and so on. Okay. Now there is a special pointer that always points to the first node of the linked list, and that is usually called head. So that's the head of the linked list, and we use the head to find out where the first node is stored in the memory. And then from there, we can find out where the second node is. From the pointer in the second node, we can find out where the third node is. Okay, so that's the overall idea. So each node, as I said, can be a class or a struct that has two member variables. It has a key or data that can be an integer, a string, a value of type double, and so on, and a pointer, usually called next, because it points to the next pointer. after next node, a pointer that points to the next node. So that will be a very simple class. And then on top of this class, we build another class called linked list. And we'll do this in the next video in full detail, but just to give you an idea. And in the linked list class, we don't need to store all this information. The only thing that we need to store in an object of linked list class is this pointer here, the head. Because if someone knows the value of the head, which is the address of the first node, then it can go to the memory to that address to find out where the first node is, and then it looks at the next in the first node, and that will be the address of the second node. And then it looks at the next variable there, and that will be the address of the third node. So knowing the value of the head, which is the address of the first node, is sufficient to find out where all the nodes in a linked list are. Now, a couple of things that is important here is that, first of all, in a lot of member functions that we implement in the linked list class, we need to what's called traverse the linked list, which means we start from the head, as I said. From the head, we find out where the first node is, and then we look at its next member variable, and that will be the address of the second node. From the second node, we look at the next, we go to, so we are walking through the linked list from the head to the first node, to the second node, to the third node. And we usually do this using a loop. And in many cases, we need to know when to stop, right? And so how do we know that we are at the last node and there is no node after that? So we shouldn't try to access the next node from the fourth node for this example, right? And the idea here is that in the last node, the next pointer is null, right? So if next is null, then we are at the last node of the linked list because there is no next. Okay, that's one important aspect, and it's kind of intuitive, right? It makes sense. The other thing is, how do we know if a linked list is empty to begin with? And an empty linked list means a linked list with no node. And usually when we create a linked list, we start from an empty linked list and then we insert new nodes as we go, and then we remove them and so on. But how do we know that if a linked list, whether a linked list is empty? And that check is very simple. If a linked list is empty, it means that it has no nodes, and in particular, it doesn't have a first node, which means that head doesn't have anything to point to. So head points to nothing, and that means that head is a null pointer. So if head is a null pointer, then the linked list is empty. Then the linked list is empty, which means it doesn't have any node. It is empty. Okay, simple observations. Now, before talking about the member functions that manipulate a linked list, let's talk about the idea of a linked list and compare it a little bit just based on this high-level description that I gave you, and compare it with arrays, okay? Now, the first and one of the most important features of an array is that the elements are stored in a contiguous area of the memory. That is not the case for a linked list, right? So I'm drawing these nodes side by side, but in the memory, they probably are not side by side. Most likely they are not, right? So the first node is here, and then the next node is here, and then the next node is here, and so on. And that's why we need these pointers to go from the first node to the second node and the third node. Okay, so the values are scattered all around the memory, not contiguous, and that has its own advantages and disadvantages. For now, if you want to talk about one disadvantage, is that we don't have random access in a linked list, because in an array, if you remember, when we have an array of size n, and if we want to go to this element, we don't have to start from the beginning, go to the second, third, and so on. We can do the math, if you remember, with the address of the beginning and the size of each node, the size of each element, and we immediately find the address of here, and then we can directly go here and access that in constant time. But that is not the case for a linked list. If you want to go to the fifth element in a linked list, you have to start from the head, and from the head you go to the first node, from the first node you go to the second node, from the second, third, and so on. So you have to traverse the linked list to get to the fifth, 10th node, and so on. And as a result, so unlike, let's write it down, unlike array, we do not have random access in linked lists. And actually, reading or writing, so reading what is the integer in the third or fifth or nth node in a linked list requires the traversal to the nth node, and that takes some constant times n, because from the head you find the first node, from the first node you find the second node. So n steps to get to the nth node, and then you can read the data and return it or change it. So reading, writing takes, instead of constant time, takes order n time, where n is the number of nodes. Okay, if you want to see the first value in the first node, that's fast. But if you want to see the thousands or 2000s and so on, then it takes you a while, because you have to traverse to that node to see what data is stored. Okay, so no random access. Reading and writing the value in the nth node takes order. Okay, now let's talk about some of the basic operations that we have. So linked list operations. So this is the interface that we want to have. And these are the operations that we are going to revisit later on when we use linked list to implement other data structures as well. Okay, so the first one, and these operations, depending on where you look, have different names. So the first one is what's called push front. So you want to add a new node with this argument as its key to the beginning of a linked list. Okay, sometimes it's called insert at front, or insert at first as well, or push front. Okay, it's a void function. It doesn't return anything. It just adds a new node with the key as its key to the beginning of the link. Okay, so as I said, today we are not going to look at implementation. We just want to familiarize ourselves with the ideas, and then in the next video we will talk about the implementing all of this in C++. Okay, so let's say this is your linked list with 3 nodes, and the data that you have currently, you have 10 here, 7, and 12. And what you want to do is you want to push front for this linked list. You want to push front, let's say 9. Okay, so how do we do that? So the first thing that you need to do is you need to create a new node using dynamic memory allocation, using the new operator. So you say new node, create me a new node, and then it returns a node star that I'm going to call P or PTR. Okay, so when I do that, it creates this pointer P that points to this newly created node, okay, which is going to be my first node. okay? Because I'm pushing this to the front of the linked list. Then what? Then I use this pointer P, which is returned by the new operator, to write 9 as the key or data for this node. So I say P arrow data equals 9. So I write 9. Now what's left is connecting this to the rest of the linked list. Okay? So first of all, if you think about it, this pointer here should point to what used to be the first node, which will be the second node after the push is complete, right? So this pointer should point to this node here. So the question is, where can we find the address of this node? And that's easy to, find out because we have this head pointer that contains the address of the first node. So if I say something like P arrow next is equal, assign head to P arrow next. So head is the address of the first node. I'm assigning the address of the first node to P arrow next, which means that next is now pointing to what used to be the first node. So now this is my first node, this is the second node, third node, and fourth node, and this is empty or null, right? Now, the final thing to do here is that now since this blue node is the new node, is the first node now, right? The blue node is my new first node. Head should point to this because remember I told you head is a special pointer that always points to the first node in a linked list. Now, this node that contains 10 used to be the first node, but not anymore. This is my first node now. So I should change the value of head so that it points to this node here. So head equals. Now the question is, where can I find the address of this node? And again, that's easy. It's just P. And that's it. Now we're done. Okay? Now if you think about it, whatever we did, creating the new node and then changing the pointer and changing the value of head, these 3 steps, they don't have anything to do with the size of a linked list, with the number of nodes in this linked list. The time that it takes to push front 9 into this linked list is independent from, how many nodes you have here. It could be 10 nodes, it could be 10,000 nodes, it doesn't matter. Which means that you can do this in constant time. So push front can be done in constant time, which is the best you can expect, right? You can hope for. All right, so that's good. Let's push front. Now the next operation that I'm going to look at is called top front. Now these names, we are going to see them for a lot of different data structures. So we have top and we have pop. Usually top, it depends. In some programming languages, they're implemented a little bit differently, but usually top returns the top element, the first element, and pop removes the first element without returning anything. But sometimes pop removes as well, but top returns the first value without changing the data structure, okay? So if I call top on this 9, 10, 7, and 12, it returns 9 without changing anything about the data structure itself. But if I call pop, it removes this node entirely. So it's kind of like the opposite of push front, and it doesn't return anything. It's a void function, okay? That's usually the case, but sometimes pop, after removing, it returns 9 or returns the entire node. Okay, so top front. Now, how do we do that? Let me not draw, because it's very simple, and let me not draw a picture for it. So let's say we have this 9, 10, 7, and 12 as our linked list, and I call top front, so it should return 9. And how does it access 9? It uses head. I forgot to update. After this line, head will be pointing down here. Okay, so it doesn't point to here. So, okay, so I use head and I say head arrow, whatever the name of this variable is, usually it's called data or key. So head arrow data is what this function is supposed to return. So it's even simpler than the previous one, and obviously it's constant. Okay, that's the 2nd operation. The next one, as I said, the one that removes the first node. pop front. And let's do the version that it doesn't return anything. Okay, so let me draw an example. This is the head pointer pointing to the first node pointing to the second node. Let's say we have only 3 nodes for simplicity, because it doesn't matter in the computation. So first of all, if you call this on an empty linked list, it should throw an exception saying that there isn't anything to remove. Same with top front, right? If there is no node, then you should do something different, right? But that's something that we deal with next time. Okay, so pop front. So it's supposed to remove this node, right? Now, you might think that if I just change this pointer head so that it points to the second node, then we are done, right? So, and that's easy to do. We can just say head is equal to, not equal to, I mean assign, right? Head arrow next. So head arrow next is this pointer, which is the address of this node. So if I say head equals head arrow next, basically what I'm doing is that I'm saying, okay, head is not supposed to point to that node anymore because I'm changing its value. And from now on, I want to store this, which is the address of the second node in this head pointer, which means that head is pointing to here, right? And remember, head is always pointing to the first node. So if head is pointing to here, this is my new first node. And it seems like I've removed the what used to be the first node, right? But it's not quite right to do it this way for a reason that I will elaborate on. Okay, so changing this pointer using one line of code. Now it's like we bypassed the first node, or what used to be the first node, and we directly go to this, which means that head goes here and this goes here. So we have only 2 nodes. The first one is here. The problem is that we didn't manage the memory right. These nodes are created dynamically when we insert them. Remember here, right? And if you remember, when you do dynamic memory allocation, it's you who is supposed to deallocate the memory when we are done. Now, before doing this, I have to remove this using delete, right? So, or deallocate, that is a better term. So before doing that, deallocate the memory allocated to the first node. And when you do that, then you can say head equals head arrow next, and you're set. Okay. There's a little bit of trick. You need a temporary pointer here, but we will talk about that in the next video when we are dealing with the details of it. But in any case, you'll see that again, the things that we do here, deleting this node and then changing the value of this head pointer, doesn't depend on the size of the array. So this is also a constant time operation. Okay. So everything is ideal so far. All the operations are constant time, which is perfect. But if you want to do something similar, like push or top or pop from the back of the linked list, then things get a little bit ugly. So the next operation that I want to talk about is a push operation. But this time you want to push something to the back of the linked list. Okay, so you have this linked list, has the head pointer, some data, next pointer points to the next node, data, next pointer points to the next node, data is 10, and then this is null. Okay, so a linked list with 3 nodes. And then we try to push back a new value to the end of this linked list, let's say 9. Okay, so how should we do that? Now, first, similar to push front, I create this new node using the new operator. So I create a new node somewhere in the memory. I'm drawing it at the end, but it could be somewhere. We don't know where that would be. But when you do that using the new operator. So we say create a new node, and then it does that, and it returns a pointer that points to that newly created node. So node star PTR. So this is PTR pointing to this, right? Then I need to write 9 here. That's easy. I said PTR arrow data or key equals 9. And then I need to set this to null. That's also easy because this is going to be the last node. So it's next point. Remember the point that we mentioned up here, right? The next should be null in the last node. So that's easy also. We say PTR arrow next equals null. So 2 lines of code for setting this node up with 9 and empty or null. The final thing is this pointer here, which used to be null, should not be null anymore because this node, the third node, is not the last node anymore. This is the last node. So I need to change this null pointer. But the problem is, how do I access that, right? And I'm not going to write the code for it. That's for the next video. But conceptually, what you need to do is you start from the head, and then you say head equals head arrow next. So that head now you go here, and then from here you go here. So you need to traverse the linked list as we talked about up here, right? Order n time to traverse the linked list and reach the last node. So you start with a temporary pointer that also points to the first node, and then you move it along from the first node to the second node, third node, until it reaches the last node, which takes order n time. And then you say, okay, temp arrow next, which is this pointer, equals PTR, right? So after the traversal, you say temp arrow next equals PTR, which means that this pointer won't be null anymore. It points to here, and now we are done. So we have some constant time to create this last node, constant time, 2 lines of code to set it up with 9 and empty. But then to set up this pointer so that it points to the last node, we have to traverse the linked list, and that takes order in time. So overall, the dominant or significant part of the work is the traversal, which takes order in time. The rest is just constant that we ignore in the asymptotic notation. So that's pushback, order in time, which is slow. Next, we have popback. So 5 popback. So removing the last node, again, you can see that I don't want to go into the details of this one because we are going to repeat this when we are implementing it, but you get the idea now, right? You start from here, you traverse to get to the last node, and then use the delete operator to deallocate, and then probably set this pointer to null, and so on. Again, the majority of the work is the traversal, the rest is constant time, so removing the last node is also linear in time. Order n time. N is the number of nodes in all these operations. Okay, and 6, top back, returning the key or the data in the last node. Similarly, you have to start from the beginning, traverse all the way to the end so that your temp pointer is pointing to this one, and then you say return temp arrow key or temp arrow data to return this 9 at the end. So again, some constant time tasks plus the traversal, which is order n. So overall, again, this one is also linear time. Okay, so these are the main operations. There are other operations like inserting something in the middle and so on. The list goes on and on, but these are the basic ones, and we are going to implement them in the next video. But before we finish up, there is a possibility for improving the performance of singly linked lists, and that is what's called singly linked lists with a tail pointer. Okay, so the idea is that you have this head pointer that points to the first node, and the first node points to the second node, and so on. 2, 1, 7, 5. And then you have another pointer, special pointer called tail, that always points to the last node of the linked list. Okay, now this is an interesting idea, and it helps improve the time complexity of some of these operations at the end. Okay, so for example, here, if you want to push back some new key, then you create a new node here with k and empty and so on. But then you don't need to start from the beginning and traverse all the way to the end, which was the time consuming part. What you can do is you can say, okay, now tail arrow next, which is this pointer, should not be null anymore. It should be pointing to this new node. So just say tail arrow next equals PTR. Okay, and that replaces the problem of traversing the linked list all the way from the beginning to the end. So with 2 lines of code, I mean, you create the node and set it up, but then you say tail arrow next equals PTR, and then you say tail equals PTR because tail is supposed to point to this node now, and then you get rid of this, right? So you see that instead of linear time, if we have that tail pointer, we can do pushback in constant time. And similarly, top back, returning the value in the last node. If you have the tail, you can just say return tail arrow data, and that will be the data in the last node. So you don't need to traverse the linked list from the beginning to the end. It takes order and time. You can do that in constant time. But for top back, removing the last node, as we will see later on, having the tail pointer does not help. For that, we need a doubly linked list to be able to do that in constant time. In the next video, as I said, we are going to implement all these ideas in C++.